Hello everyone, I am Sixun Huang from National Kaohsiung University of Science and Technology, Taiwan. Today, I want to talk about a background subtraction algorithm using Gaussian mixture models. This algorithm is part of the work entitled as the Adaptive Background Mixture Models for Real-Time Tracking and published in CVPR, short for Computer Vision and Pattern Recognition, in 1999. The outline of this lecture includes introduction about what background subtraction is and its challenges, Gaussian mixture model about defining a model that is a mixture of Gaussian distributions, modeling process about how to model the scene using the Gaussian mixture model, subtraction process about how to subtract the background from the observed image and obtain the foreground objects using the constructed Gaussian mixture model. Based on the assumption that the camera is stationary, the objective of the background subtraction is to segment the region of interest or coded foreground from the background scenes. The pictures in the first row are the original images. Those in the second row are foreground masks obtained by subtracting the background from the original images. The framework proposed in this paper for background subtraction consists of two stages, modeling and subtraction. Modeling process is to construct Gaussian mixture models for describing the scene. At the same time, the modeling process will update model parameters to adapt to the scene change. Subtraction process is to subtract the background from the currently observed image, so as to obtain the foreground mask. The idea of using Gaussian mixture model can be described as follows. Since the background has the lighting variation, for example, fluctuation of the light source, a Gaussian distribution is used to model the pixel intensity over time instead of a constant value. In addition, the background may have multiple appearances due to non-static background objects. For example, the door of the locker may be opened or closed. This leads to the use of multiple Gaussian distributions rather than a single one. If an n-dimensional random variable x follows a Gaussian distribution, its probability distribution can be expressed as this equation, where mu is the mean vector and capital sigma is n by n covariance matrix. To simplify the discussion of GMM-based background subtraction, we let x denote the gray level intensity. Therefore, mu becomes the mean value and capital sigma becomes variance, the square of standard deviation little sigma. The original Gaussian equation can be rewritten as this form, whose curve is bell-shaped. For example, let S be a random variable denoting a gray level intensity of a particular point. If the three observations of X are 3, 4, and 2, which follow Gaussian distributions, the mean value is last 3.0 and the standard deviation is 0.81. This equation shows the Gaussian probability distribution of X. As for Gaussian mixture model, it is defined as a mixture of k Gaussians, where W sub k is the weight of the kth Gaussian. The summation of all weights has to be 1. In other words, GMM is the weighted summation of k Gaussians. For example, if the distribution of X is described by the 3 Gaussians, its actual distribution is the summation of these 3 ones, as the black line shows you here. After introducing Gaussian mixture models, we next talk about how to model the scene using Gaussian mixture model. In this paper, all image points are considered as the mutually independent, and the intensity distribution of every point at any time t is modeled as a mixture of k Gaussian distributions. K is determined by the available memory and the computation power. For computation purpose, an online k-means approximation is used for modeling. Since all points are mutually independent, we will only talk about the detail of modeling a single point by Gaussian mixture model later. Given a sequence of observation, S1, S2 until St of a particular point, the objective of the modeling process is to estimate the parameters of the Gaussian mixture model, including its weight, mu, and the standard deviation. In this paper, an algorithm called the online k-means approximation is used. At initial, we have the observation S1. Online k-means approximation algorithm directly creates a Gaussian to model observation with weight equal to 1.0, mu equal to x1, and the large sigma. During iterative step, we firstly check if any Gaussians will generate the current observation xt. We call it match here. If at least one Gaussian matches xt, we update all matched Gaussian distributions. Otherwise, we directly create a Gaussian to model it. For the picture on your left-hand side, if the observation st matches this Gaussian, we will update it to fit the xt. For the right one, if the observation st does not match any Gaussians, a Gaussian in green color is directly created to model it. Here, a match of xt to the case Gaussian distribution eta is defined as within 2.5 standard deviations, as the equation in red rectangle. In case 1, if at least one Gaussian matches the st, we will update the parameters of all matched Gaussians. For a matched Gaussian, updating it means using st to adjust its parameters at time t-1, so that to make the updated Gaussian distribution more fit st. The updating flow is shown in this equation. Next, we will talk about the detail of how to update weight, mean, and the standard deviation. Firstly, we talk about how to update the weight. The weight is updated as this equation, where alpha is a predefined constant called the learning rate. For example, a Gaussian model with weight equals to 0.3 at time t-1. By giving observation st equal to 110 and the learning rate alpha equal to 0.01, the weight will be updated as this equation to 0.307. For mean value, it is updated as this equation, where rho k is the learning rate times the fitness of st to the matched Gaussian distribution. In this example, rho k can be derived through this equation, and is equal to 0.00017. Having rho in hand, we can update the mean value as the weighted summation of mu at previous time and the current observation st. According to this equation, the mean value is thus updated from 100 to 100.0017. Similarly, it updates standard deviation as the weighted summation of variance at previous time and the variance estimated by using st. In this example, It is updated using this equation. Accordingly, the standard deviation will be updated to 15.986. In case 2, no Gaussians match the current observation ST. We firstly create a new Gaussian with low weight, mean equal to ST, and the large standard deviation to model ST. Then, we remove the Gaussian with this weight if there are already k Gaussian distributions in the model. Finally, we add the created Gaussian as one of k Gaussian distributions. After introducing how to model intensity distribution of a particular point, we next talk about subtraction process, that how to classify the point as foreground or background according to the constructed k Gaussian distributions. The first step to subtraction process is to select the Gaussians that correspond to background from the constructed k Gaussians. We call this process as background Gaussian selection. Since the background intensity are the values that appears frequently, so the background Gaussians should have high weight and low variance. Accordingly, we firstly saw the k Gaussians in a descending order with respect to W over sigma. Then select the first B Gaussians as background models, whose weight summation is just larger than a predefined threshold T sub B. For example, there are 3 Gaussians and the TB is set to 0.6. We firstly calculate the weight over sigma and followed by sorting them. Since the total weight of the first 2 Gaussians is 0.7, which is larger than T sub B, so we consider the first 2 Gaussians as the background Gaussians. After determining background Gaussians, we next assign the label foreground or background to the point according to its observation ST. If the ST matches at least one background Gaussians, we classify it as background. Otherwise, it is classified as foreground. In this example, one background Gaussian is matched, so we label it as background. Next example shows that none of background Gaussians are matched, so we label it as foreground. In this lecture, we detail a Gaussian mixture model-based background subtraction algorithm. Thanks for your listening and have a nice day.